we are going to specify the following. Okay, so the heat influx is the following: partial of integral over partial T sub Q Q d little a. Okay. Now, just like our Cauchy theorem, there is an equivalent theorem that can be shown for the context of heat conduction, right, or for heat influx across a boundary, which is that if we have this, then what it has to match up on the boundary with a heat flux vector, okay, dotted with the unit outward normal to that boundary, dA, okay, and it has to be the negative of this if n is the unit outward normal. So the picture is this. Okay, so let's suppose that this now is my heat boundary. The idea is that across this heat boundary we are providing some heat input, okay, and this is that heat input we are providing to the body. Little n is the unit outward normal, okay, with unit magnitude because it's a unit vector. Okay, so what we're saying is that the heat we are providing happens as a vector, right? When we provide a certain amount of heat, capital Q, across the boundary, that gets transferred into a heat vector, here, heat flux vector, okay? And because capital N is the unit outward normal, we have a negative sign if Q is the influx, right? If capital Q is the heat influx. Okay, little q is the heat flux vector. Okay, what this means is the heat per unit area per unit time. Okay, that's what we mean by the heat flux. And this is an idea that you've almost certainly encountered previously in your study of physics and perhaps thermodynamics as well. Okay, all right, so this is the situation that we have. Okay, and let's now forge ahead, okay, with this background. The law that governs the supply of heat to the body is really a subset of a more general and important law, right? It's the first law of thermodynamics, which we have already seen in restricted form in the context of mechanics alone. Okay, so the first law of thermodynamics okay, and we are now going to state it in the context of thermomechanics. All right. Before we do that, we have to introduce one more quantity, which is a familiar quantity almost certainly to all of you. We introduce E, or rather E bar, which I will define as the internal energy per unit mass. Okay? And in the setting of thermodynamics, which we are not going to get into in tremendous detail, this internal energy is the fundamental energy that systems possess. Okay? All right. So, having done this, let's put down the first law. The first law essentially says that if you consider the total energy that the system has, right, and you define that as an integral over omega t of okay, I'm going to write first the kinetic energy. Okay, we've seen this before. That plus the internal energy. Sorry, I need to remind myself that the internal energy is not a scalar, is not a vector or tensor, it's a scalar. Okay, the internal energy also multiplied by rho, because we've defined the internal energy to be a quantity per unit mass. Okay, so all right, this integrand dV, d little v, is the total energy of the system, of our thermomechanical system. Okay, it has kinetic energy because of the fact that particles have velocities, and apart from that, everything else is the internal energy. Okay, even notions of strain energy that we've encountered before are resident inside the internal energy. Okay, it really is all the rest of the energy apart from kinetic energy. Okay, so we have this, and the first law says that the rate of change of this quantity, okay, comes from the following contributions: integrals over omega t of the work done by the forces, and we have the body force dotted with V. Okay, so that's the rate of working of the body force. Additionally, we have the possibility of internal heating. You may have distributed through the body some heat sources, right? And I should be careful about calling them internal heating. They really are external supplies of heat, but they're distributed throughout the body. And let's denote that as R bar, okay, where R bar now is heat supply per unit mass. These are the contributions that are available at every point on the interior of the body, in the interior of the body. And then we have things happening along the boundaries. Now, along the boundaries, we have the work done, sorry, this is over the entire boundary. Okay, we have the work done by external tractions, but we already know that on those parts of the boundaries where we have the traction being controlled, that traction is related to the stress through Cauchy's theorem. And on the rest of the boundary, where we are not controlling the traction, there is nevertheless a stress, okay? The stress produces a traction there, even though we are not controlling it. The stress does produce a traction, and that traction also does work. Okay? So when we combine those two terms, what we see is that we have an integral over the entire boundary of the traction due to the stress. Okay? Sigma n, as we've seen before, is a traction. We've seen this often enough. Sigma is a Cauchy stress, that dotted with the velocity. Okay? Plus, or sorry, in this case it's a minus, the heat supply, okay, which we saw on the previous slide is given by minus q dot n. All of this integrated over dA. Note that once again in the context of the heat supply, we saw on the previous slide that we may be controlling the heat supply over only the heat influx boundary subset. Over the rest of the boundary, however, there also is some heat exchange with the surrounding, okay? And that term is also given by minus q dot n, allowing us to write this integral over the entire boundary, okay? This is the first law. If we look carefully, what we're seeing on the left-hand side is a rate of change of energy. On the left-hand side, we are seeing evidence of the rate of working. Okay, those two terms are the rate of mechanical work. And these terms are the heat supply. Okay, so in a form that you've probably seen before in your study of thermodynamics, the rate of change of energy of the body is the rate at which you're doing work upon it, mechanical work, plus the rate at which you are supplying heat to it. All right, so I've introduced one new term here, which is R bar, so let me define it. R bar is the heat supply per unit mass per unit time, of course. Okay. All right, this is probably a good place to stop this segment. When we come back, we will work more with our statement of the first law.